Ready? Okay. All right. So today we are going to start with a clarification for counting sort. So the counting sort algorithm that we have covered yesterday, it was not stable because we were just keeping track of appearance of elements in the input array, and then just by looking at the counts we were producing the output array. So the version we covered, it was kind of a simplified version and it was only working with numbers. However, this doesn't mean that there is no way that we can implement counting sort in a stable fashion. So today, first I want to cover stable version of counting sort so that we can use it with any type of objects, and if we don't want to use the initial order, again, it can still be useful for us. So let's start with the input array with some repetitions. Let's say we have 3, 5, 4, 2, 3, 3, 8, 2, 7, 1, 3, 2. How many elements do we have? 2, 4, 6, 8, 10, 12. All right. So now the first step is the same. So let's go over the steps before we start. Obviously we have range of our input which is small enough to fit in memory. That's why we can use counting sort. Like, that's the first thing that we should check. If they cannot fit in memory, the range of the numbers are large, then we cannot use counting sort as it is. And then we initialize the counter array with zeros, representing at the beginning we didn't see any appearance of any elements. And then we iterate over the numbers and update corresponding counter for each of them. Up to this point, there is no change for the algorithm. So let's go ahead and generate our counter array. It's dying, let's switch. Right? Alright. 4, 5, 6, 7, 8. 6, 5, 3, 2, 1, 0. So at the beginning we start with 0 for each count, or for each counter. And then we see 3, so we increase count of 3 by 1. 5, we increase count of 5 by 1. 4, increase count of 4 by 1. 2, increase count of 2 by 1. 3, increase count of 3 by 1. Another 3, increase count of 3 by 1. 8, this becomes 1, 2, this becomes 2, 7, this becomes 1, 3, this becomes 4, and 2, this becomes 3. So what we had done yesterday was, after we generate this count array, we basically traced over this array, and based on appearance of numbers, we populate our output array, right? So here we actually kind of lost our relation with our input array, right? So we don't know the real initial order of elements that actually have the same value. And what we can do differently is, so instead of generating output based on the counts in the counter array, first we can accumulate the values in the counter array. Meaning, starting from the beginning, we add our number to the next one. So instead of keeping track of count of elements of 3 or element of I, what we keep track of is how many elements have we seen so far before this point. So now let's generate the accumulated count array. So how many elements do we have up to 0? 0, right? How many do we have up to 1? 0. How many do we have up to 2? 3. So basically the way we do this operation is we add count I minus 1 into count I. Like this way we can accumulate it all, as we will see. So how many elements have we seen before 3 so far? 7. Like basically we accumulate the previous element into ours. How many elements have we seen before 4? 11, right? Or actually, it's including 4. And here it's going to be 12, this is going to be 12, this is going to be 13, and this is going to be 14. So, right now, after we generate the accumulated array, based on looking at these numbers, we can detect on the latest position of this number, or the first position of the next one. So what would be our desired output based on this? Let's generate it, and then we will see how we can get that from the input. So it's going to be, we have 0, 0, 0, 1, and then 3, 2, 2, 2, 2, and 4, 3, 1, 2, 3, 4, 1, 4, 1, 5, 0, 6, 1, 7, and 1, 8. Oops.
7, 8.
1, 4, 1, 5. This is 5, right? Is that correct?
Yeah,
But we had one, I guess we missed updating this one. Okay. Or I think it's gonna be better to get rid of this at this point, because I don't want to update all the accumulated numbers here. Okay, so is this correct?
No, no.
2, 3.
11 must be 8.
What's that?
11 have to be 8.
11 have to be 8. This one?
7, 8. 9.
Ah, okay, so we had error in accumulated array. Okay, thanks. Let's update these guys. Okay, 7, so this is going to be 8, this is going to be 9, this is going to be 9, this is going to be 10, this is going to be 11, right? Okay. So, let's see how we can go from this to this. Like right now, after generating the accumulated array, what we do is we start iterating over our input. But we don't have to do it from beginning to the end. We can start from the end, because right now we keep track of the end position of each element in the accumulated array. So, the last element we see, it is 2, right? So we go look at inside of 2. What does it say? 3. So it means we can, the 2's are ending right before 3. Meaning we can place these 2 into the second position in our output. So let's say this is our output 1. Now let's see how we are going to generate output 2. So we generate output 1 with 3A, right? We just went over the counts and then generated. So now we are going to look how we can generate output 2 with 3B. So we started from the end, and then we looked at the accumulated array. And the accumulated array told us, okay, so 2's are ending at 3. So we place this 2 to right before 3, which is 2. Let's put the indices over here. It's going to make our job easier. 6, 7, 8, 9, 10. So we place this 2 over here. And then what we do is we decrease our position by 1. So now, instead of 3, we are going to have 2 here. And we continue. So we see 3. What was the end position for 3? It was 7, right? So we place our 3 into 6, and then we decrease this by 1. Because we have placed 1 3, right? That's why we decrease this accumulated array count. And then we continue. Now we have 7. What was the last position for 7? 10 minus 1, 9. So we place 7 to 9, and then we decrease this by 1. And then we get to 2. So now the count of 2 is 2, meaning we should place our 2 into cell 1 and then decrease this by 1. Or another thing we can do is we can basically replace the order of these operations. and then do the decrease at first, and then place directly to that number, right? It's going to be the same thing. So we see 8. First we go to the place of 8. We decrease it with by 1. And then we go to 10 cell, and then place 8. So we are at 3 now. We go to the third count cell. We decrease it by 1, and then we place our 3 into 5th cell. So we see another 3. We go to the count, we decrease it by 1, and then we place it to corresponding cell. 2. We go 2, and then we decrease it by 1, and then we go place our 2 into the corresponding cell. 4. We do the same operation. To the 7th cell, we place 4. 5. We do the same operation. To the 8th cell, we place 5. And finally, 3. So we come to 3, we decrease it by 1, and then we place the last 3 in here. And as you see, we kept the order of the input for the elements that have the same value for our comparison function, right? Like the first 3 ended up here, and the last 3 ended up here. So the order within values that have the same value for this sorting, it is preserved. It was the same with our input. So that's why it is possible to implement counting sort in a stable way. Yes?
Why go through all this trouble just to make the algorithm stable? What is the benefit?
Depending on your application. Because if the problem asks you to use counting sort like an algorithm, but they care about the order of elements in the case of having the same value and preserving the input order, then you have to use something like this.
I know. Is there
Or another one is, yesterday we see, for example, radix sort, right? Part of radix sort was actually using counting sort. Like in radix sort, what we were doing is we were starting from the least significant bit and then sort the numbers using counting sort, right? And for that it was important to be stable. Because once we go to the next digit, if they had equal value on the digit, then we want to keep the previous order. Because like, let's say when we are evaluating numbers, I think with an example it's going to be more clear. Let's say we have 10, 13 and 19. And let's say they were in this order. So once we are sorting them with radix sort, what we are going to do is first we are going to look at the least significant digit, right? And then we sort them by this digit. So they are going to be like 10, 13 and 19 after this. So now, when we are looking at the second digit, if we do not keep the previous order, if we place, for example, the second one before the first one, then we may end up 13, 10, 19, and which is not going to be the desired output, right? So in order to have successful radix sort, the counting sort path that we are using in the radix sort has to be stable. And we will also see, like today, some of the problems we are going to solve, they will also require this feature as well. So in that case, it will be useful. And again, like the reason I'm showing them both is it definitely depends on the application that you want to use the sorting algorithm for. If the application does not require any kind of stability, you don't have to deal with all this stuff, right? Because the 1 to 3a part is very simple. And you don't go through this accumulated array and try to make, oh, was that -1 + 1 kind of thingies. It's simpler. But depending on the application you have in hand, in the case of radix sort, for example, you may need a stable sorting algorithm. So that's why it's very important to understand what the question is asking from you, so that you can come up with the easy to implement and simple solution. Any other questions? All right. So let's go over radix sort once again. because that part I think may not be very clear. Yesterday we didn't put stress on it. So when we are sorting the input with counting sort, it has to be stable, or any other stable sorting algorithm you can use. And the reason is, as we mentioned here, like if we lose the previous order, then it's going to cause us trouble. Because first we sort them by the least significant digit. And as we go further, once we see the same value in a more significant digit, we should keep the order that was determined by the least significant or less significant digits. That's why like stability can come into play for some problems. And in the case of application of radix sort, it is important. So any questions so far about counting sort or radix sort? No? Okay, cool. So today we will continue with more sorting practice. So I picked 3 questions for you. After you finish those, we will continue with more. But let's start with these 3. I think you guys all have access for the slides. Like I just modified the previous lecture slide. Or you can search them by name on the as well.